Welcome to Paradise Lesson 140, and today we're finishing off the second half of this podcast series. So back in the last podcast 139, we covered the theory of winglets, which we can see here, and the potential benefits for having winglets that can adapt to different flight conditions. So you're flying perhaps in cruise or in takeoff, and these winglets will change their shape to adapt to that. So if you haven't listened to that other podcast, 139, I recommend that you go back and do that because it'll make this podcast much easier to understand. You can find that in the link in the description, or actually the card up here actually. And we also found in the last podcast that changing the winglet angle had quite a decent effect on the lift coefficient, but not so much on the drag coefficient. So this winglet can actually rotate around the wingtip, so it goes from like clockwise or counterclockwise. And from the CFD setup from the last podcast and the validation process, I concluded that the error in this drag prediction is about 5%, whereas for the lift it's about 2%. So if we see differences greater than these amounts, respectively, then we can conclude that these results are trustworthy, that if the changes in the drag coefficient are greater than 5%, then the CFD is good enough to trust. And if it's greater than 2% in the lift, then the CFD is again good enough to trust. Anything below these errors probably needs to be taken with caution. And I should probably re-mention what this paper is that we're looking at, just so you can refresh your memory and find it in the link description below, because it's open access as well. So this paper is New Aerodynamic Studies on an Adaptive Winglet Application on the Regional Jet CRJ 700. So in this podcast, we'll be going through in more detail the effects of these different winglets on the CRJ 700 airplane performance. And in the last podcast, we looked at just the general effects. So the authors say that ideally the winglets will be pivoted to the angle that will yield the greatest aerodynamic benefits for each flight condition. As such, it is important to know how the winglets at each angle affect the airplane's lift and drag coefficients across the flight envelope. So the flight envelope is like how the airplane can fly. So for example, if you have different altitudes, different Mach numbers, and different angles of attack, etc. So in figures 9 and 10, we see the maximum changes at each winglet deflection angle, so each winglet pivot angle around the wingtip, as shown in the proportions of this figure. So in figure 9a, for example, this is the maximum change that we see when we have different flight conditions for a winglet angle of, let's say, 0 degrees, 35 degrees, 73 degrees, 93 degrees, etc. Then in 9b, we have the average change that we saw across this entire flight envelope with different winglet pivot angles. And likewise in figure 10, we have the maximum and average drag changes. So let's talk about the lift coefficient to begin with. So for the lift coefficient, the greatest changes that the winglets produced across all the flight conditions looked at, which in this particular case, they range from -2 degrees to 2 degree angle attacks for the entire wing, which is like regular cruise. So across all these flight conditions, the maximum change that we saw in the winglets was 3.28%. And this was when the winglets were deployed down at an angle of 35 degrees. So that's quite funny because winglets are almost always deployed upwards. So having them deployed downwards to produce the greatest benefit to lift is just a funny thing. Well, interestingly, we should also note that if a winglet is pointed downwards, this is called droop. And it's not that common, but we do have a name for it still. And as we saw in the last podcast, if the winglets are completely flat, the airplane exhibits a greater lift coefficient than if they are angled. This doesn't make much sense to me because having winglets flat would really just be like having a longer wing. And a longer wing doesn't really produce that much more lift in terms of the lift coefficient. The only ways that I can see that this happens is if either the winglets airfoil profiles were different, so that they do produce more lift than a regular wing of the same airfoil profile as the actual wing, or perhaps the researchers didn't take into account the change in the wing reference area. So they used the old reference area, which would be smaller, but when you put the winglets horizontal, you now have more wing there, so that's a greater reference area. So this in figure 9a, we see that if the winglets are deflected at even 0 degrees, so it's completely flat, or -35 degrees, so down a little bit, drooped a bit, we get 3.2 to 3.28% increases in the lift coefficient. So that's quite interesting. But if you have any ideas why this could happen when the winglets are not really vertical up or down, I'd like to hear them in the comments below, because these are just two ideas that I had. One, that they didn't take into account the different reference areas, or two, the winglets had different airfoil profiles that did actually result in, okay, we did have simply more lifts being produced from that little bit of additional winglet acting like a regular wing. What is also interesting is that as the winglets are pivoted at more extreme angles, their effectiveness on the lift coefficient reduces. So we can see here when we go to either being completely vertically upwards or completely vertically downwards, this results in like only a small reduction, actually, even in the lift coefficient of minus 0.5%. So not only is it not very much, it's actually a reduction. Now, I should mention that because this percentage is so small, it does fall within the error, so this reduction may not actually occur, but it's just interesting to note. Let's move on to the average changes now that we see with this winglet deflection angle across the flight envelopes on the average lift coefficient. So in figure 9b, we see that even if we look at the average effects of the winglets on the lift coefficient of the airplane, having the winglets either drooped at 35 degrees, so this one here, the third column, or completely flat, so that middle column, results in the best lift coefficients with the lift coefficients boosted by 2.4% on average. So that means that if you put your winglet, this particular winglet, either completely flat or drooped a little bit at 35 degrees, it doesn't matter which part of your flight you're in, so it doesn't matter the Mach number, the altitude, I guess the angle of attack does matter, but we'll get to that in a second. But it doesn't matter whether you have different altitudes or different Mach numbers. The winglet will be, on average, increasing the lift coefficient by 2.4%. And this is a pretty good boost across the entire operation range of the airplane. And I should mention that, again, this 2.4% is above the 2% error that I concluded from their validation study from last podcast. So this 2.4% is in earnest. Interestingly, any deviations away from these two angles, though, from 0 degrees or minus 35 degree droop, results in a dramatic drop-off in performance. So you can see as soon as we go to minus 73 degrees or plus 35 degrees, we get a drop of at least 1% and even more, 2% sometimes. And interestingly, if we go to being completely vertically down or completely vertically up, again, we actually get a reduction in the lift coefficient, which is about minus 1%. Again, this is below the error percentage, so this may not really occur, but there's potential there for that to occur. So that's the lift coefficient. Let's take a gander at the drag coefficient now, which is figure 10. And for figure 10a, which shows the maximum change in the drag coefficient with the different winglet pivot angles, we see pretty much across all pivot angles of the winglet, there is a reduction in the drag coefficient. However, it should be noted that all of these changes fall within the drag error I concluded from the last podcast. So we can see here that, okay, so we do find that even when we have a winglet of 0 degree deflection, like pivot angle, so it's completely flat, we get a reduction in the drag coefficient of 2.73%, which is very nice. The problem is that this is within the drag error still, which I concluded was about 5% in the last podcast. So these reductions can't really be taken as certainties. It has to be taken with a grain of salt. And to be perfectly honest, it doesn't make sense to me that we'll get such a great drag reduction at a 0 degree winglet pivot angle. The reason why is because, okay, if you do put the winglets at completely flat, you are artificially increasing the aspect ratio of the wing because you're now grouping the winglet into the wing in terms of the lifting profile, into the lifting reference area, so that's actually producing lift. But it's not going to be that much because you already have the wing which has like a aspect ratio of maybe 10. And if you put an additional little winglet on there, it might be going up to 10.5, 11 maybe. So that's going to increase the efficiency of the wing, but not necessarily the lift coefficient that much. So let's move on to the average effects of the winglets pivot angles across the flight envelope for in figure 10b. And we see here that almost all the changes to the drag coefficient hover between minus 1% and 1%. So like last podcast, I find this very interesting because unless there is some kind of fancy airfoil profile the winglets have, the changes in the drag coefficient should be more pronounced than this, I think. So winglets, even in cruise, do produce a decent amount of drag reduction in terms of the induced drag. So, for example, when the winglets are completely flat, this is effectively just a wing with a slightly greater aspect ratio, while when greater aspect ratios do increase the wing's efficiency, you need significantly greater changes than the ones here. From what I can tell from these winglet geometries, to get a good drag reduction. So if you just were to increase the aspect ratio, whereas if you were to put the winglets vertically up or down, that is much more effective at reducing the induced drag than having a greater aspect ratio. There are also different reasons as well, for example, different structural loadings, etc. And you can also design the winglets to reduce the structural loading if you design them to produce different moments. But so there's a differences between using winglets and increasing the aspect ratio. Regardless of all this, I would expect for the average changes across the flight envelope for winglets, even at this angle of attack of 2 degrees, for there to be like, a 5% change in the drag coefficient, maybe 10%, maybe that's maybe a bit too high, maybe 5%, 7%. Here we're seeing like almost nothing. It's like between -1 and 1%. So another potential argument as to why changing the winglet's pivot angles doesn't affect the drag coefficient too much here is because maybe the winglets don't produce much lift while they are completely flat. That argument hinges on the idea that if there is little to no lift being produced at the wingtips, there is no pressure difference between the bottom and top surfaces of the wing. And if you remember from last podcast, I was telling you about how this pressure difference drives this drag. So just in a nutshell, if you have a low pressure on top and a high pressure underneath the wing, you get air bleeding over from the bottom surface to the top surface. That creates a wingtip vortex. This wingtip vortex is effectively wasted energy because you're not using it for anything. Now that's a simplification I should mention, but I'm not going to go into the advanced aerodynamics here for that. You can take advantage of this wingtip vortex if you try, but generally speaking, it's a bad thing. It's just wasting energy. So that's how the wingtip vortex occurs. So if you have now at the wing tips a profile of the wing that doesn't produce much lift or any lift, that would then result in almost a zero pressure difference between the lower surface and upper surface around the wing tip. That will dramatically reduce the amount of bleeding of air going around the wing, which would then reduce the wingtip vortex. That's the only other reason why I can think that at like 0 degree angle of attack, when you put the winglets at 0 degrees, so they're completely flat, why we might get almost a nothing change in the drag coefficient, or like it's the same amount as if we had the winglets upwards. But that's a bit of a long shot, so I'm not really sure why we here we're seeing that we don't get much of a change whether the winglets are vertical or horizontal. So let's move on from here. I think that it's mainly just errors in the CFD. Let's move on to the drag polars just to see what they look like. So let's go down a little bit here. So figures 12 to 16 show the drag polars of the CRJ 700 at different velocities ranging from Mach numbers of 0.31, which is this one here, all the way up to 0.79, which is up here. This is a side note. The drag polar is a graph where the drag coefficient is on the x-axis and the lift coefficient is on the y-axis. These graphs are arguably the most important graphs in aerodynamics because they show so much basic information about how efficient an airplane is. So these graphs are arguably the most important graphs in aerodynamics because they show so much of this information. In a nutshell, the more lift an airplane can generate while producing the same amount of drag, the better it is. And you can see quickly if an airplane does that on a graph like this because you have the lift on the y-axis, and if it produces more lift than another configuration, all that happens is that the line will move up. So if the line moves up, we can tell that, okay, the airplane is now producing more lift for the same amount of drag, which means that it's more efficient. In addition to that, the drag polars are also very useful for determining the maximum lift to drag ratio. And you can find that by drawing a straight line from the origin to the steepest part of the graph. And this steepest part is where the airplane has a maximum lift to drag ratio. And the slope of this line is also this number 2. So if you were just to draw it to the steepest part of the graph, and then you calculate the lift to drag ratio from the lift coefficient and the drag coefficient, you then get the lift to drag ratio, and you can tell whether one airplane is producing more efficient than another airplane. It's very easy to do. So this maximum lift to drag ratio indicates the most efficient flight condition for the airplane given the Mach number and altitude. And for all of the Mach numbers presented here, the adaptive winglets shift the line upwards, which means that the airplane's aerodynamics is improved. So we can see here at figure 12, when the Mach number is 0.31, so it's really low, the lift coefficient is increased, as it is in this plot, this plot, this plot, and this plot. So all Mach numbers. As we have seen from other plots, the winglets really aren't affecting the drag coefficient too much. So this improvement is really just a function of the improved lift coefficient. So figure 18, let's move on to that now, shows a pretty cool way of visualizing the effects of the different pivot angles of the winglets. The effects that these have on the lift and drag coefficients and the lift to drag ratio at different angles of attack of the plane's wings. So we see here, figure 18A has coefficient, drag coefficient, then lift to drag ratio. And this ranges from 1 degree angle of attack of the wings to 4 degree angle of attack. This is for a Mach number of 0.5, which is, they mention is the lowest cruise velocity effectively. Interestingly, at 4 degree angle of attack, the winglet pivot angle now has quite a large effect on both the lift and drag coefficient. So we can see here this top line for 18A and this top line for 18B corresponds to when the angle of attack is 4 degrees for the lift and drag coefficients respectively. For example, if we look at figure 18A, the minimum lift coefficient seen across the different winglet pivot angles is about 0.77, which happens about here when the winglet is pivoted completely upright. And we get a lift coefficient of about 0.77. The maximum lift coefficient we see is about 0.91, which happens when the winglet is pivoted at about minus 25 degrees downwards, so it has that droop. And we get a lift coefficient of 0.91. That means that at an angle of 4 degrees, changing the winglet pivot angle from minus 25 degrees to 90 degrees or 93 degrees, we get a change in the lift coefficient by 18%. 18% is now we're getting into the actual range that winglets can change the performance of an airplane by, and this makes much more sense to me. So this change, though, may be too high, and this depends on the exact reference area they used to calculate this coefficient. As I've mentioned before, I don't know whether they used the reference area of the wing in general and used that for all different winglet configurations to calculate the lift coefficient, or whether they calculated the projected area of the wing with the winglet at different angles and then used those reference areas to calculate the lift coefficients. I'm not sure which one it is. In the former, that is actually wrong because now you have an artificially low reference area, which would then artificially increase the lift coefficient just through mathematics. The way you should be doing it is you should get the winglet at whatever angle it is pivoted at, then project that area onto the ground, and then calculate what that area is, then use that area in your lift coefficient calculation. So I'm not sure which one they used here, but we can conclude that this change in the lift coefficient is up to 18%, depending on whether we had the former or the latter way of using reference areas. Let's move on to the drag coefficient now, because we also see some interesting changes here now. So as the wing's angle of attack increases, the effects of the winglet's pivot angle on the drag coefficient becomes greater. So we can see at 0 degree angle attack, here, this 1 degree angle attack, there's almost no change. As we go up, we do get a significant change. The maximum changes are seen at a 4 degree angle attack. Interestingly, there is an offset in terms of the best and worst winglet pivot angles between the lift and drag coefficients. What I mean by that is that the winglet pivot angle that produces the best lift coefficient, which was about minus 25 degrees, doesn't correspond to either the best or worst drag coefficients. So likewise, the winglet pivot angle corresponds to, so when the winglet pivot angle that corresponds to the worst lift coefficient, which is 93 degrees, this doesn't correspond to either the best or worst drag coefficient either. So there is an offset here. Here, the lowest drag coefficient and hence best drag coefficient is seen at a winglet pivot angle of 75 degrees, while the worst drag coefficient is seen when the winglet is pivoted directly downwards. So 93 degrees downwards. In fact, the best coefficient is about 0.0525, while the worst drag coefficient is 0.059. That means that the winglets are reducing the drag coefficient by 11% in the best possible configuration compared to the worst possible configuration. And this is much more reasonable. This is much more similar to what we expect. Finally, and then we have the lift to drag ratios. And finally, the best lift to drag ratios are seen when the winglets are completely flat. So I'm not too sure why exactly that is. As I mentioned, I think it's probably because the reference area that they use for lift coefficient is incorrect, which gives us this effect here. And comparing that to the worst lift coefficient, the worst lift to drag ratio, winglets are improving the lift to drag ratio in this configuration by a whopping 20%, which is really good. This might partly explain why we weren't seeing much of a change to the lift and drag coefficients earlier. Those data were for angles of attack between minus 2 degrees and 2 degrees, which are lower, but still I feel that there should be a better change than what we saw for these angles of attack. So that's the end of this podcast, and that brings us to the end of our podcast. I should mention my little aerodynamics, and if you liked it, make sure to hit the like button, and if you want to see more like this, hit the subscribe button. And if you want to get better at CFD and or theory like this, check out courses in the description. And if you want to make your experiments 2 to 4% more accurate, check out Atmosphere Hawk. The reason why this instrument, it's an instrument that we make, and the reason why this instrument makes your experiments 2 to 4% more accurate is because the density of air changes every day by 2 to 4%. That's just nature. Like if you get to your wind tunnel at 9 in the morning and you start doing experiments, you then come back after lunch and you do more experiments, the change in your density will be between 2 and 4% in that time frame, just within a few hours. That comes down to changes in temperature, barometric pressure, and humidity. And unfortunately, most aerodynamic wind tunnels do not take that into account. That means that when you do your force measurements or whatever, even you're checking the velocity of the wind tunnel, that is wrong by 2 to 4% through the density of air that's being carried forward, the error in that. Now, things get even worse when you go between days and weeks and months and seasons. As we all know, most experiments don't really start and end on the same day. They'll usually go for days, even months, and even seasons. I think the longest experiments I ever did was like 6 months or so. And over that entire period, the density of air might change by 15%. That's quite normal. So if you're not taking into account the change in density of air, you're getting artificially wrong. You're getting wrong results, and you don't even know it. So the Atmosphere Hawk is actually make 2 accurately measured density of air for you. And it's being used by quite a lot of researchers in research, and also recently in not just aerodynamics research, but other research that does require aerodynamics knowledge in sports science, actually. So that was quite fun that we started to make contacts in that field. But anyway, you should check out the Atmosphere Hawk and get one for yourself to make your experiments more accurate. And it also makes your CFD validation more accurate because you now have accurate data. You'll find that instrument in the link in the description. And I'll see you next podcast. Peace, amigos.